Yeah, welcome to 24 Hours of Pass Summit Preview 2018. We are excited you could join us today for Dejan Sarka's session, a sneak preview, Advanced R. The 24 Hours of Pass consists of 24 consecutive live webinars delivered by expert speakers from the Pass community. The session will be recorded and posted online after the event. You will receive an email letting you know when recordings are available. My name is Satya Tianti. I'm a data platform MVP, also a speaker and a helper, volunteer in most of community conferences. I have few introductory slides before I hand reins over to Dejan. Next. Okay, this is most important thing. If you require technical assistance, please type your question into the question pane located on the right-hand side of your screen, and someone will assist you. The question pane is also where you may ask the question throughout the presentation. Feel free to enter your question at any time. And once we get to the Q&A portion of the session, I'll read your question aloud to the speaker. You're also able to zoom on the presentation content by using Zoom button located on the top of the presentation window. Please note that there will be a short evaluation at the end of the session. Your feedback is important to us, so please take a moment to complete it. This will pop up after the webinar ends in your web browser. Next. I would like to take a moment to thank our presenting sponsor, Quest. The staging of 24 Hours of Pass would not be possible without their generous support, and they are the reason this event is available free of charge. If you would like to learn more about Quest and sign up for information how they can help you, please visit sponsor page of 24 Hours of Pass website. Next.
Hello?
Yeah, next, Dejan. Next slide. Can you hear me? Hello? Yeah. Okay. PASS is a global not-for-profit association where data professionals connect, share, and learn. Joining PASS is free, gives you access to hundreds of hours of free online content, live, virtual, and in-person events, the ability to join your local groups in your area, and the opportunity to attend annual conference, PASS Summit. PASS is a great way to connect like-minded professionals, increase your technical expertise, and grow your career. Next. The 24 Hours of Pass session is presented by Dejan Sarka. Dejan is an independent trainer and consultant that focuses on development of databases and business intelligence applications. He is also an MCT and data platform MVP. Besides projects, he spends about half of the time on training and mentoring. He is a founder of Slovenian SQL Server and .NET user groups. Dejan Sarka is a main author or co-author of 16 books about databases and SQL Server. Dejan Sarka has also developed many courses and seminars for Microsoft, SolidQ, and Pluralsight. Next. And without further ado, here is Dejan with a sneak preview Advanced R. Over to you, Dejan.
Okay, Satya, thank you very much. Just the last check, can you hear me well?
Yes, loud and clear.
Okay, great. So thank you everybody for joining this session. This is a sneak peek preview of the Advanced R seminar, which I'm going to do as a pre-con seminar at the PASS Summit 2018 in Seattle. So during the seminar, I will make an overview of the whole project lifecycle, of the whole data science project lifecycle, from introducing the problem through data overview and preparation, the modeling, where I will use many different algorithms, the model evaluation, and even deployment and using the model for predictions. Now in this sneak preview, I will just pick up some topics from each area. So of course we have limited time, so I will just show you some limited topics, so you will get the idea how the seminar will look like, and also the presentation should be somehow self-standing, should be also enough for you to get a brief understanding of a data science project. So let me start by introducing you the virtuous life cycle of a data science project. So you start with identifying the problems. For example, let's say that you are you have some online banking and you realize that some transactions are fraudulent. So you identify the problem. So next step, you transform this problem into a model. So you use your existing data and prepare it and transform it to a model which will give you some predictions on new transactions. So this transform part is the part where you actually do the data science activities, which I mentioned in the previous slide. So once you have some model selected, then the next thing is to act. This, of course, means to deploy the model in production. And deployment can be as simple as just creating some graphical or textual reports to give you some more understanding about patterns and so on, or of course, deploying it in your transactional application to perform online predictions on the new data so you can react really in real time. Now, the project is kind of never finished because, of course, fraudsters do learn. So the patterns you extracted in the transform part will actually change over time. So at some point, you have to realize that your model, which you are using in production, is becoming obsolete. So you must measure the quality of predictions all of the time, compare it with the actual frauds. When you see that there is a gap, the gap between the predicted and the actual frauds is rising, you have just identified a new problem. So it means you go back to the initial stage, you just identified a new problem and you need to refine the models. Now this transform part has its own inner cycle. In this part, you start with business understanding. This is, of course, connected to identifying a problem. And then you must deeply understand your data, doing all kinds of graphical presentations, statistical analysis, and so on, and prepare your data. Typically, you don't have data from your transactional system completely prepared and suitable for statistical data mining, machine learning analysis. Data preparation and data understanding will actually take you about 70% of time you dedicate to the whole project. And then you do some modeling, which means you are implementing different algorithms with different parameters on your data. And then at some point, you need to decide which model is the best, which model is prepared for the production. So you must evaluate the models. And when you select the model you will use, you go to deployment, and this is then connected with the act stage from the previous slide. Now, typical question is, how much time does it take? How do you know if you have the best model? The problem here is that you will never know whether you have the best model already, or maybe if you would spend 10 more minutes, you would find a better model. But remember the previous slide, we have the whole cycle of a project, which means we are also measuring the quality of predictions over time. So you can even refine your model even before they become obsolete. You can use this infrastructure also for a constant improvement of your predictions. Now, this was a brief introduction, so let me skip to R. Of course, because this is a little bit more advanced, session and a little bit more advanced seminar. In the past summit, I will not go really and spend a lot of time with R basics. So I will just go directly to this data science part, which means that I will start with the data set. This is what you analyze. So you collect all of the knowledge you have about your cases, which are entities or observations, and use their variables, columns, attributes of these cases for analysis. Now, how is physically represented the data set in R? Typically, the most popular representation is a data frame. So data frame looks like a SQL Server table, although please note it is a matrix, not a table. It is a matrix with columns where each column can have a different data type. So what does it mean? Compared to a SQL Server table, in a data frame, you have positional access. You can retrieve data, let's say, from row 5, column 3. You can also use column names, but you have positional access. The order is maintained. So, for example, if you don't change the order of a data frame, you can make projections, split it vertically, and then join it again by just binding the columns row by row, because our data frame maintains position. Okay, now let's go directly to this data preparation and data overview. So first you have to realize what kind of measures you have in your data values, whether your variables are discrete, so they can take a value only from a limited pool of values, or they are continuous through numerics. And discrete can be further categorical or also called nominal, or they can be ranks or ordinal. Ordinal variables or ranks, they do have some internal order. Like, for example, when we will finish this session, you will be asked to fill the evaluations, and these evaluations, you will use ranks, I don't know, from 1 to 3 or 1 to 9. They have an order, but arithmetic on these ranks makes no sense. And continuous variables can be limited, meaning in their intervals, limited on one or both sides. This is very, very typical in business. Of course, for example, income, typically it is interval from 0 to whatever, but hopefully it doesn't go below 0, the income, right? And then we can have true numeric variables that support all kinds of arithmetic. You have to realize what kind of variables you have in order to properly inform the algorithms what kind of data they have to deal with. For some algorithms, for example, if you use Nair-Bayes algorithm for predictions, it can accept only discrete values. For example, if you use some regression, linear regression, regression trees, you must have some continuous variables. There are also some specific types of variables. Constants are typically useless because they have no information, as we will see very soon in them. They don't tell us anything. The lowest possible amount of discrete values in order to have a useful variable are 2, of course, binary variables or dichotomous variables. Monotonic, like ever increasing row number, maybe you have some identity property and so on, could be also useful if you have some logic in these values. For example, in general, you can say that higher identity value means that this piece of data, this row or this case came into the system later than the one with the lower identity. I know it's not 100% sure. Of course, you all know that you can set identity insert on and then insert identities with lower number than the last one in your data is currently. But in general, like in 99% of cases, you can say that higher identity value means later case. So it might be also somehow useful in your data model. Now in R, when we talk about discrete variables, in our terminology, we call them factors. And each different distinct value from this limited pool of values is called a level. And levels can be ordered. So if you order the level, you have to inform R about ordering the level, or about order of the levels, then you get ordinal variable. Now, it's really important to correctly define the order of ordinals, otherwise you lose this internal meaning and you cannot find maybe some associations with other ordinal or continuous variables. What if you have algorithm, you want to use algorithm like logistic regression, naive Bayes, which expects discrete variables, and you have many continuous variables. So you do the discretization, or also called categorization, binning, sometimes even recoding. So you discretize this continuous variable into a limited set of discrete values. You do it many times to make data comparable. Let me tell you an anecdote. Years ago, I was involved in a research about phone calling habits in European Union countries. And one of the variables we used was also call length. Well, it turned out that it was really hard to compare call length between different countries, because in some countries average was very, very short, and in some countries, namely, of course, you can imagine Italy, the call length average was much longer than in any other country. So how do we compare this data? Well, with discretization to three categories, long, short, or medium length call, we had comparable data, and of course, this discretization was done country by country. Now, we have many possible discretization methods. I will mention just three. Typically, when newcomers come to this area, they start with equal width discretization, which means they are making classes of equal width. So, for example, if we have age from, let's say, 20 to 100, people will make maybe 5 classes. Each one will be 20 years width. Now, this might be useful because it kind of preserves the distribution, but from analytical perspective, you will see later, I will prove you later, that you are losing more information than with equal height binning. Equal height means that you have equal number of cases in each class. And of course, the width of these classes varies from class to class. This is the binning that preserves the maximal possible information. So this is what you use if you have no clue about business meaning of the data, and this is then quite safe choice for preserving the information. But many times the best is to use business logic or real life logic when you do the binning, especially in these variables you get from business like income and age. What does it mean? Business or real life logic? Well, you know that, let's say with income, $100 or 100 euros makes a big difference if you earn 300 per month, and really doesn't make a big difference if you earn 30,000 per month. Also, like 1 year makes a big difference if you are 15 or 16, but it really doesn't make a big difference if you are 65 or 66. So in this case, this age income, you would discretize in such a way that you start with narrower classes at the bottom end, and then you make wider and wider classes at the top end. Now, let me switch to my demo, and let me show you a couple of these options I talked so far about. So I will also share this code with you. I already installed all of the packages I will need in this demo. So you run this code only if you don't have these packages installed. And I loaded already in advance all of the library. some of them are quite big, like parties, so it takes some time to load them, and I wanted to be sure that I'm ready for this presentation. So now I will read the data. I actually stored data in a comma-separated values file, but this is actually the data from the target mail view from target mail view from the Adventure Works DW demo database. You see, I already loaded data in memory in the top right part of the screen. Let me just quickly show you how it looks like. Don't bother about the small font, it's not important what's inside, just to see that it looks like a table, but it was a data frame. Now, let me try to, there is a variable called education. Let me try to make a plot or bar chart of this variable. And let me zoom it. And you can see that it's somehow weird. This distribution doesn't look very close to the real life distribution, because of course it should, even if it's discrete, it should somehow represent Gaussian. Of course, what is wrong, I didn't inform R that this is an ordinal, that this variable actually has an internal order. So I declare it as a factor. You see, I have here parameter. When I read the table strings, this factors equals true. So it means that my data frame will immediately recognize all strings as factors or discrete. But I didn't inform about R about the order of levels of education. So I will just use the function factor to define the levels in this order. So let me execute this line of code, and let me do the plot again. And now you can immediately see that the distribution is more in accordance with real life. It does resemble a bell curve, and it simply means that it's now everything prepared to use this variable in more advanced algorithms. Now we have also variable age in years. I think the age goes from 28 to 99 years. People are getting quite old in this Adventure Works DW database. So at some point we will have to change the birth date to get slightly younger people again. But anyway, equal with binning, in this case I will do binning in 5 bins. It's very simple. In R you can use function cut. So I will just add a new variable to my target mail view. I will call it HEWB, like equal with binning, and this will be H cut into 5 bins. And with table function, I will simply show you this textual representation. You see at the bottom left, you see I have bins from 27.9 years to 42.2, and these intervals are open on the left side, and so it means left value is not part of the bin and closed on the right side. So the 42.2 value is part of the first bin, not the second bin. And you also see the distribution is somehow weird. So we have nearly 9,000 pages in the first bin and only 33 in the last. So let me try to do the equal height binning. There is no function from the core R that will do equal height binning. I will just use my own function. Remember, this is kind of advanced R, so we will not be afraid of writing our own functions. Although, of course, in R there is already around 12,000, I think, additional packages. So I'm pretty sure it's quite easy to find the function that does equal height binning for you in some of these packages. But let me do this step by step. So first, I will use integer division by 5 to see what should be approximate number of cases in each bin. So it's 3,696. Now I will create these 5 bins, each one with 3,696 cases, and but I have some additional cases, leftover cases in my data set. So let's see how many they are if I do modulo 5. So I have 4 additional cases, which I will simply put into the first 4 bins. So you see, I will add a case to first 4 bins. So this is how I develop my function, and everything I have shown so far, step by step, is included in this function, binning equal height binning, which is another function. And it accepts 2 parameters, the actual data, so it will be a vector of values and number of bins, and then it will split the data in this number of bins. So let's fill this function with h from my target mail view, and let's add a new variable to my view called HEHB, or H equal height binning. And let's see now the distribution of this variable, and you see, as I expected, I have 3,697 cases in first 4 bins and 3,696 cases in the last bin. Now, custom binning, I can again use the cut function from the core R, and I can simply give this function as a second parameter, not the number of bins, but the actual boundaries of this bin. So very easy. Let's see now. And you see again, we have left intervals that are open on the left side and closed on the right side. And you see that I have somehow custom binning, means narrow classes in the beginning from 27 to 33 and wider at the end from 65 to 90. Now let me show you the distribution of these 2 variables, histogram. I will not use plot function, but I am using Eric's histogram from the RevoScale R package. So this is already a package that comes with Microsoft R Server or with R services or machine learning services in database with SQL Server. What is the difference compared to, for example, plot function that I used earlier? Well, there is one big difference. This is very scalable. Of course, with 18,000 cases, which I have here, you cannot really feel the difference. But if you would have millions or even billions of cases, believe me, you would see the difference very, very quickly. And you see that this histogram shows you that with equal width binning, we really get some kind of weird distribution. With equal height binning, you see clearly that, of course, now why it's called equal height binning, is equal number of cases in each bin. So it looks like this picture looks like a perfect square. And custom binning is somehow the most logical in this case. Okay. Now, remember when I said that with equal height binning, you are preserving the maximal amount of information. Can we measure this? Of course, from information theory, we have a measure for Shannon-Wiener information theory. We have a measure for the amount of information or amount of uncertainty in a system. So we calculate the probability of each state and multiply it with logarithm of this probability, and then we summarize this this calculation for all possible distinct states, and then we multiply this by -1 because probability is a number between 0 and 1, and logarithm on input between 0 and 1 is negative. Now you can imagine that if we have a constant, then the probability is 1 and logarithm of 1 is 0, so constant has no information in it. The more equal distribution you have, the more uncertain is the outcome. Just imagine, not even going, I will show this calculation very soon in a demo, but just to give you the explanation. Now, just imagine that you have dichotomous variable, two states. So, for example, now we are getting into world football, or as American says, world soccer championship. So we can, let's say, make a bet that Brazil will be world champion. Yes, no, we have two possible states. So if we have a distribution like probability that Brazil will win is 90%, then it's really hard to lose this bet. But if it's 50-50, then the uncertainty is the highest possible. So this information doesn't really even help you much, the distribution. You will be surprised in half of the cases. Now, with more possibilities, now let's say that we have three possibilities for a world champion. We have three possibilities, let's say Brazil, Argentina, and Germany. And please, nobody gets offended, but these are like very strong teams. So let's say Brazil, Argentina, and Germany. Again, if we have distribution like 90% probabilities for Brazil, 5% for Argentina, 5% for Germany, you would bet on Brazil and uncertainty would be very low. But with one-third probabilities, then again, the uncertainty is very high, but even higher than the uncertainty in previous case where we had two states. In previous case, you would be surprised only in 50% of cases. Now with three possible states, you would be already surprised in 2/3 or 67% of cases, which simply means that more states means that you have more information. So this is why when you discretize, you are kind of losing information. But if you discretize in equal case beams, then the loss is the smallest possible. So you preserve as much entropy as possible. So if you don't have a business logic, then the next, let's say, best thing from analytical perspective is to discretize to buckets with equal number of cases. But please understand, if you want to preserve the distribution, then you would go to equal width with enough states, and then your bar chart should somehow be close to the continuous distribution, to the plot of the continuous distribution scatter plot of your variable. Now, before I go to actual analysis, let me actually calculate the entropy. There is entropy function in one of these libraries I loaded in memory in advance. It uses the frequencies distribution of my variable. So let me quickly calculate these tables again and store them in variables, their distribution you saw. And now let me calculate the entropy when I did equal width binning. So first value here, 1.6 is the actual entropy. Second value is the maximal possible entropy when I have 5 cases. So this would be the case when I would have 20% of probability for each state. And this is the actual entropy divided from the maximal possible. So you'll see that I kind of lost 30% of entropy compared to the maximal possible entropy. Let's do the equal haste binning, and as you could imagine, I preserved maximal possible entropy. So the actual entropy is equal to the maximal possible entropy of a variable with 5 classes. With custom binning, it is a very, very nice intermediate option. So I preserve both business logic and quite a huge amount of entropy. You can see that I lost only 6% of entropy, which is very good in this case. Now, let's imagine that my data is prepared. Of course, this was very short, and I just picked up entropy for this demo. In the seminar, we will do many, many other things besides discretization. We will do some summarizations, we will deal with missing values, with outliers, and so on. But for this short presentation, just to give you the taste how the seminar will look like, I just picked up discretization and entropy. Now imagine my data is prepared, so I will do some analysis. In general, we split the algorithm, divide the algorithm in two broad classes: directed or supervised data mining or data science and machine learning, and undirected or unsupervised. Supervised or directed means I have a target variable and I want to explain the values of this target variable with input variables. And this explanation, this is the actual model I'm creating. And using this model means I use this explanation for classification or estimation of target variable in a new case. So typical methods are classification for discrete variables, estimation for continuous, forecasting, which is typically the same thing as estimation, just the estimated value is in the future, so you cannot check how good the estimation is immediately. You have to wait till this future and then you will see how your estimation was good. Undirected means you are kind of just fishing in the mud to see if there is anything useful there. So very typical is affinity grouping, market basket analysis, clustering. Even some advanced descriptive statistics is already part of this analytical processing. Now I will introduce two directed classification algorithms, and then I will compare these two algorithms. So let me just brief you, without going really in depth in mathematics, represent logistic regression. So we start with input. These are input variables or input units. And then we combine those input units in a single value. And then we do another nonlinear transformation of this value to get another value, and we define this as an output. So in this central unit, what we do, we combine input values typically with weighted sum, and then we do some nonlinear transformation with so-called sigmoid or logistic function. That's why we call this logistic regression. So what we get with this function is a value between 0 and 1. And then we say this is our prediction, okay? And let's say that we have two possibilities: binary target variable, true, false. And we say if the value is greater than 0.5, then my prediction is true. Now, how good these predictions are, I will talk about measures of quality immediately. So the next algorithm I want to present is the most popular algorithm in data mining or machine learning for classification, the decision trees algorithm. It's also called recursive partitioning. We have many additional flavors of this classification trees or decision trees. I will just use one or two algorithms in my demo, but in the seminar, we'll also talk about decision forest, random forest, etc. So how does it work? Imagine I have this data. I have a movie, and I asked people who watched it whether they liked it or not, and I also asked them about their age, class, and education level. So initially, 55% of people liked this movie and 45% didn't. So I want to see whether there are some specific classes of people that like this more. So the algorithm tries every possible split on every value of every input variable. So you see I'm trying, you see the green line that is moving across the rectangle. So I'm trying all possible splits in such a way that I get the purest possible classes of target variables. So it turns out that initial split was done on age. People older than 35 years mostly liked the movie, like 73% liked of them liked, and people with lower age didn't enjoy the movie so much. And then I continue my splits. So the next split will be done on education. And in the first class for older people, let's say we do the split with in the education level 2, whatever does it mean, let's say high school. And people with high school or more like the movie even more, while less educated people didn't like it. And then I do the same split with the younger people, and again with the second split was done at the education level of 5. Even if they are younger, with higher education, apparently people like the movie. Now this is my model, and how do I use it for predictions? Well, I simply take a new variable, a new case, check the education level and age, and see in which class does this new case fall. So let's say that this is a person that is like 25 years old and with let's say graduate degree. So it will fall in the bottom right class. So I will have like 67% of probability that this person will like the movie. So how do I measure quality of these predictions in advance? Of course, we already know from introduction part that we will always measure these predictions over time. So we will see how good these models are over time. But during the evaluation part, we have to decide which model we are going to use and to deploy in production. So for predictive models, this is kind of a simple thing. You simply split the data set you have into two subsets called training set and test set. And you build the model using the training set, and then you use this model to make predictions on a test set. But in a test set, you have the outcome of the variable you are predicting already known. So it's very simple to measure how many times the predictions are correct. You typically do this split in such a way that you use 70% of data for training and 30 for testing. This is not really high mathematics behind. This is something that is that comes from real life projects. It works well, so more or less everybody is using it. Although if you use 75-25, will not be so much difference as well. Well, the only important thing is that you really do this split randomly. Otherwise, you are building some pattern in your data. Now, once you have this data split, you do a classification or confusion matrix where you simply check how many times the actual positive predictions were really positive, the negative predictions were actually negative, etc. And then from this confusion matrix, you can make many derivatives, many additional terms, calculations, or graphs. Very, very popular are receiver operational characteristics or ROC curve or leaf chart. So let me show you briefly a confusion matrix. So we have 4 classes in this matrix. True positives, bottom right, means positive predictions that were actually positive. True negatives, negative predictions that were actually negative. False positives, predictions were positive, but the actual value was negative. And false negatives, prediction was negative, but the actual value was positive. Which part is the most important depends on a business problem you are solving. So for example, if you are doing a marketing campaign and you are only interested in a question who will buy your product, then the only important things are true positives. The more true positives, better model. But for example, fraud detection is more complex because your best customers are their purchases are many times similar to frauds because might be business people that travel a lot, so they make many purchases for, let's say, plane tickets, which are quite expensive. So they do many purchases for quite high amounts in different cities in a short time. So you might predict that some value is a fraud, that some case is a fraud, but it's actually not. So this is false positive. So you cancel, let's say, the credit card and you just lost your best customer. So when you do fraud detection, you have to also compare false positives, not only true positives. Now, then you can make many different different additional calculations. So depends again on your case, or you can do even more complex calculations like harmonic mean, or let's say ROC curve, receiver operating characteristic curve, which is actually plotting true positives against false positive rates. And in case which I mentioned, fraud detection, this is extremely useful, very simple to use. The thin line here that goes across the square is like a random guess line. Means if I would select a case from new cases and randomly guess whether this case is fraud or not, I would be in general accurate in 50% of cases. And you can see the lift from this curve by the actual models. So higher distance or higher lift from the random line, like in this case, the blue line simply means better model. So let me go back to my last demo, give you more information about my data. So I will predict the bike buyer column, and I will inform that this is a discrete variable. The R would initially think that this is a numeric integer because we have values 0 and 1. So I will make labels no and yes. And I will prepare my test and train data set. So 70% for the training and 30% for the test. Let's see the distribution of bike buyer in both sets. You can see that in both cases that it's about, let's say, 51, 52% of non-buyers. If, let's say, the distribution would be extremely different in training compared to tested, then probably the split was not done really randomly. So I will use function GLM to model bike buyer as dependent variable and yearly income, age, and number of cars owned as independent. So I will just create the predictions with predict function using the test dataset and my model. And remember, logistic regression gives you values between 0 and 1. Let me just show you what I got. I got these probabilities. So for case 3253, the probabilities, the logistic regression value is 0.36, which means this is a non-buyer. So let's create a factor out of it, and let's see how many of those were declared as true. And here is I create the matrix comparing actual and predicted values. So I have 1604 true positives and 7053 true negatives, but I have quite a lot of false positives. So let's do some more models. So for example, airpart function comes from the basic installation and is this decision trees, recursive partitioning, and we have C3 function which comes from the party package I loaded, which have C3 function, and this is again decision tree. So let's make some predictions and let's see how these decision trees were behaving. And you can see that this is somehow better compared to logistic regression, 1604 and 1084 false positives here. Actually, true positives are not much better, but false positives are much better. So in this case, I would probably use my decision trees instead of logistic regression. So let me add a column called prediction to my data set. Now, when I have everything in my data set, I can, for example, calculate additional terms like remember from slides accuracy, and I will not really go into details how you calculate this, but this is combination of true positives and true negatives. So I was correct in 63% of time when I used my decision trees model. I can also see the probabilities. I use probabilities for my ROC curve. And let me just show you ROC curve. So this is my ROC curve for my decision trees model. In this case, it's still not very good lift. In the actual seminar, I will do many more models and try to improve this curve more and more. Lift chart.
Dejan, sorry to interrupt you. We have nearly 3 minutes to go.
That's perfect, because this line of code I'm showing is actually the last one, and then I will simply wrap up. Thank you very much, Satya. It's perfect timing. Thank you. So lift chart is just checking the true positives. So for example, if I would have marketing campaign, then I would be interested in lift chart only. And again, I have a random guess line, the bottom line, and the two lines for different models. So the black line is for logistic regression and the red for recursive partitioning. And remember that with true positives, logistic regression was not really bad. So for this case, I must even decide to use the logistic regression instead of the decision trees. As I said, there are many different measures. If you remember from this slide, there are many different measures. You can make even more derivatives in the actual seminar. I will show at least 10 different derivatives from the confusion matrix. Which one you use really depends on the problem you are solving. Let me just give you one more example. So in the past, at some point, I worked with some university. We tried to predict landslides. And in this case, these false negatives were extremely important. So what does it mean? You simply predict there will not be a landslide here, and then people build houses there, and then landslide happens because of your false negative. And of course, people lose all of the property and maybe even lose their lives. So now we have a couple of minutes for questions. And Satya, did you get any questions?
Not at this point. The question pane is blank at the moment, so we'll just wait for attendees to type in their questions. Thank you.
Okay, thank you very much.
Sorry, I don't mean to rush you actually in the last minute, but wanted to get the...
Yes, thank you very much. It was perfect.
We'll just give another minute or so for people to type in question. Okay, there is one question about how do you use strings in regression?
How do you use strings in regression? This is the question. Well, you must make some kind of variables, continuous variables out of them. By the way, you can always use discrete variables in regression trees. So regression trees work with discrete variables like decision trees. They make splits, and then they calculate regression formula in each subclass. So you get piecemeal linear regression, which might be very useful for some predictions or estimations. But if you really want to use linear regression, so if linear regression is like a regression tree with no split, then you must have continuous variables only. So you must do some data preparation, like, I don't know, maybe calculate some weight of each string, maybe using length of the string, or create even more complex calculations, like if there is a string with less common letter in it, you get higher weight, or with less common syllable, depends on the language. But immediately you can use factors or strings in regression trees.
Okay. We have one more to go. We'll give opportunity for one more question. I mean to say. Okay, can you highlight something about annealing in machine learning?
About what?
Like annealing, ANNEALING.
Can you write it down, or?
Yes, it's ANNEALING, annealing.
I'm not really.
Okay, we can follow up that anyway, I think later on. But there is another question. In physics, loss entropy means more order. So it surprises me that in this context, low entropy means that variable is not worth further analysis. Could you clarify, please?
Yes, it's the same thing. You see, less entropy means more order, but more order means less surprise. So less information. This is completely aligned with physics. More order means you have nothing, you cannot learn nothing new. Let's say if you have a constant variable, then you really cannot learn nothing new from this variable. So it doesn't give you any additional information in prediction. So let's say that your input variable age is, you have only a group of 40 years, exactly 40 years old people. This variable doesn't really help you in any explanation of the target variable. Age is then useless. Entropy is the lowest, but information is also the lowest. Or, I mean, completely ordered means no, complete order means no information. So it is in alignment with physics.
Okay. Yeah, yes, thanks. That's fine. Okay, on that note, I believe we just kind of short of time on the questions. So could you please put on the next slide, Dejan? Okay, so thanks for coming up for this webinar, but stay tuned for the next session, Data Science in Cloud with Leila Etati. And I would like to thank you all for attending, and thanks Dejan for enlightening us. Thank you.
And thank you also in my name for attending, and thanks, Satya. And just the last sentence, I will get all of the questions later, so I will try to reply over email for any additional questions. So thank you very much.
Wonderful. Bye.